Yes, sir.
Okay. That's fine. All right, now it should be okay, I believe.
Yeah, it's okay. It's back.
Okay, all right, thank you. So yeah, please, so let me
You're
know if
welcome,
you,
sir.
okay, thank you.
Okay.
Thank you. I appreciate people letting me know. I do not want to talk and have no one see what I'm talking about. All right, so let me go back and make clear what I was talking about. When you come to this page, I did mention I do want everyone participating to register for this class on this page. This page has all the course materials. We can download the materials here on this button here. I'm going to download this one so you can see. I will try to make all materials in PDF so that you only need a PDF reader. So I will not go through this in detail, but I will say that finite elements is a very powerful method for numerical solution of partial differential equations. In this class, we will focus on practical solution of 1- and 2-dimensional partial differential equations using software. First, we will use some special software called FEM, which is well-designed software that is especially used for finite element method. Then we will do a simple program ourselves in using Python because Python is a good general purpose computational tool. I do have some course texts here, and I will make these available on the web page. Software is here. At some point, you will need to install all of this software. These you will have to use the download links, or next week I will bring some USB and you can install from USB. Here's some different course topics. You can read yourself. I don't want to take the time now, but you can read these yourself because you can download this document yourself. Okay. Any questions about the course? Any questions? Okay, well, let's move on to the next. Next is course introduction. Okay, let me download and we can do from there. Okay. So let me make this full screen. Okay. Okay, actually, I think, oh, here we go. Okay, all right, so this is Introduction to Finite Elements, Theory and Practice. I realize that some students are PhD, some students are masters. I will be starting with basic mathematical background. So the first week will be more involved with a theory and mathematical background. And then the next 2 weeks will be more involved with programming. Certainly you need to have mathematical background in order to be able to do the programming. Okay, so here's what I will talk about: the course web page, course materials, method of instruction, evaluation, and computer issues, and something about myself. Okay. All right. I hope that you all have this link I have set by WhatsApp. I will be assigning homework. You will turn in homework at this link, at this class. So materials will include the course text. I will also post lecture notes, exercises. I will post also the videos for the sessions. There's software, as I mentioned before, FEM and Anaconda. And most of these materials will be shared on the course Canvas webpage. That's the webpage I showed you here, this webpage here. Now, as I mentioned also, large software can be downloaded or will be shared by USB. If you shared by USB, you must have antivirus installed to receive the software. Okay. Okay, all course communication will be shared through this group. I will add the PhD group as well because I know there are PhD students. Okay. All right, so my method of instruction I would call active or interactive. I do not want to talk and have people not understand what I'm saying. So I want to make sure that you understand. So for this reason, during class, you will be working on problems. So I hope that everyone has something to write with and some paper. So during the first part, I will review some material. Then during the next part, we will work some exercises together. And then during the next part of class, I will break you into groups, and you will be able to work together on some exercises that I will indicate. Then I will ask for 1 hour of homework every day because this is a very compressed class with much material. So you will need to do some work outside of our session together. Okay. Please come to the class, prepare to work, and bring your paper and pencil. Okay, any questions? Let me see if I can do something here. Can I get the chat maximized here? I guess not. I'll have to work out how to use this better next time. Okay. All right. Homework, I encourage you to work together. Please make your answers short and direct. I do not need long answers. Most answers will be 1 or 2 sentences. Sometimes I will ask for some mathematical formulas or demonstrations or derivations. These will not be very long or complicated. I do want to make sure you have some basic understanding of the concepts. When you submit your homework, you can either submit a text or you can photograph your writing and send me the photographed copy. Just a little bit about myself. I do have some experience in many different areas. I got my bachelor's from Princeton, my PhD from Wisconsin. After I finished my PhD, my PhD specialty was applied probability. I went and taught in China for 5 years. Then I came back to US and I did also a second degree in physics and did some research in physics. Then I worked as a systems engineer for Motorola. Motorola, you may know, at one time made cell phones. They made one of the first cell phones and developed cell phone technology. So I worked as a systems engineer for Motorola for over 10 years. And then I joined my current institution, which is Texas A&M Central Texas up here. I also have a great deal of experience teaching in Africa, including, as you can see down here, Sudan, Nigeria, Cameroon, Benin, South Africa, and I think that's most of the countries I've been to. You can see my family at lower right. I have 4 children. They are all grown. Probably some are older than you. My son, Joseph, and daughter Esther, Lydia, and Rebecca. And here's my wife, who I met in China. Some of my publications. My area of mathematics is really not very well defined. Best way to say what I do is industrial mathematics. Industrial mathematics means mathematics that is applied to current interests in industry and technology. This is different from applied mathematics, which can still be very theoretical. Working on industrial mathematics means that I do a great deal of collaboration with people who are outside of mathematics, especially computer scientists and other engineers. So you can see some of the areas that I've worked in: machine learning, groundwater prediction. This one is the demographics or statistical analysis of social data. This one is design of a system using drones for agricultural monitoring. Then this one is more theoretical. Then network design and various other applications. In my mind, mathematics is a tool that is used to enhance other areas. Mathematics is a language that must be spoken in order to make advances in technology and science. So my interest is in helping other people understand this language. And there are many opportunities in this area. So I have several current projects. My most recent project has to do with COVID and COVID control. So I recently wrote some papers with students on this subject. And this also involves the solution of a system of ordinary differential equations, and mostly I look at numerical methods. Also, I do some more demographics or social statistics, more with machine learning, and network design, and some other areas as well. All of these projects I work together with students. I do like to develop students' capabilities. Okay, so thank you for attention, and I wonder if anyone has any questions. All right, now I really do need some feedback, and I'm not sure how to make that work. Let me look at the chat here. Okay, good. Okay, so okay, so please, can I have everyone type something in the chat so I can make sure that you are of the chat? Okay, I want to make sure that everyone has access to the chat window. Please type something there. Okay. Is somebody speaking? All right, I don't see anybody typing in the chat window, so I'm not sure what is happening.
Trying to type in, but it's not going.
Oh, it's not going? Okay, all right, good. Are you typing? You have to type below where it says to everyone. There's a blank space there. Okay, I've got 3 people so far. And I have, I think, over 10 people. So I need to get some more response.
I've done that.
Please.
It's going now.
Okay. All right, good. Okay. Yes. Okay, I got 1, 2, 3, 4, 5, 6,
It's going,
7. Okay. Okay, all right, very good. Okay. Yes. All right, so it looks like we are getting some responses here. Okay, so let me move on to the next sharing, the next thing I will share, which is the, let's see. The next thing I will share is the introductory survey. So what is the use of finite elements? And this presentation is not mine. I took this from the internet, but I think it has some valuable, some valuable insights in how the history of finite elements and how it is currently used. Okay, so let's do this on full screen. Oops, let's see. What's that show? Where's full page? Okay, full screen. So let me put this on the side. Okay. All right, so you can see here a number of structures. And also you can see here what you would call a heat map. For instance, on this picture on the upper left, you can see these gears which are turning. And you can also see the colors. And the colors have a code. You can see 9,000 is the maximum, 0 is the minimum. Blue is for low values, red is for high values. This is called a heat map. I am not sure what the colors represent, perhaps stress or temperature, I'm not sure. But you can see that this diagram shows the gears and how the stress is varying in those gears as they turn. This is a solution of a partial differential equation in 3 dimensions. And the solution was found by finite elements. One of the characteristics you can notice is that the shape of these gears is very irregular. The boundary is not a simple shape. Finite elements is especially adapted for cases like this, when you have very irregular region that's not smooth. Right? So you can see several examples of this. Here's another piece of machinery. And this is a semiconductor. I'm not even sure what these are. But these may show, as I said, these may show temperature, they may show stress, they may show some other quantity that varies throughout the object. So that's common use of finite elements. So finite element analysis is a numerical method solving problems of engineering and mathematical physics. It's useful for problems with complicated geometries. As I said, the shape is very difficult. Loadings and material properties. So it's often used for things or items that are under stress, but not all. It's also used a great deal in electromagnetics when you want to solve for fields. It's also used in areas like petroleum engineering when you want to know if you're trying to find the petrol under the ground and the shape of the cavity that contains it. Okay. So and it's a numerical method where you do not get an analytical or exact solution. Right? It's also not a series expansion. It's a local method that finds solutions locally. Okay, so here's usually when you do an analytical solution, you need to make many, many simplifications. For instance, if you want to model a beam or some object, a beam, which is a three-dimensional object, may be modeled as a line. The mass, which has a very complicated distribution, may be modeled as a single point. Right? So these are great simplifications that enable an analytical solution. However, the analytical solution is not exact and not very accurate. Finite elements has much more complex, and the accuracy requirement is much higher. So for this, you need to understand the physical derivation of the equations. That's one part that I want to emphasize. But once you have the equations and change into numerical form, most of the hard work is done by the computer. Okay. Right. So finite elements was first applied in aerospace. Of course, you know when you have an airplane, it's very important to know the stresses and the forces involved in airplanes, because if you are 10,000 meters up in the air and your airplane suddenly breaks, that's not a very good situation. So you do need to have a very exact idea of the stresses and forces involved. Finite elements was enabled by the development of computers. Okay, it's very, very much dependent on computers. So here are some different applications of finite elements. Okay. So the key to finite elements is discretization. So you take a real-world situation, you get a physical model, turn it into a mathematical model, and then you discretize. What does discretize mean? Discretize means you take something continuous, right? So maybe I can show you this. Okay, so go forward. Here and go here. Okay. So what do I mean by discretization? Okay. Now I can start out with a simple one-dimensional example. And I've used some example that you may be familiar with. Suppose you have a smooth function like this. Okay. And I want to find the area under this function. Okay. Now, if this is f of x, and I'm going from 0 up to L, then I'm trying to find the integral from 0 to L of f of x dx. That's going to be the area. Okay. All right, now, so to find this exactly may be difficult if f of x has a difficult form. So I'm trying to find this area here. Now, what you typically do to evaluate this numerically is a process of discretization would be you take regular steps here. Here, this length could be delta here. So the length of all these steps is delta. Okay. And then you take this, you take these here. And perhaps the simplest way to do this is to take boxes. So I can take this, oh, there's one here also. I can take these boxes. I'll take this box or this rectangle, right? This rectangle has an area. This rectangle also has an area. This rectangle also has an area. And so on. Okay. Now the height of this rectangle would be f of 0. The height of this rectangle would be f of delta. Height of this rectangle would be f of 2 delta. All right? So if I want to get a discrete approximation, instead of an integral, it would be a sum, right? I'm not sure how many intervals there are here. Well, the total length is L, and the length of each segment is delta. So here would be L over delta. Sorry, I mean it would be, sorry, I should have an index. I'll say J. J is my index, equals 0 to L over delta. Okay. And if I want the rectangle, if I want to find the area of the rectangle, I need to take the height, which is going to be f of j delta, times the width, which is delta. This is what's called a Riemann sum. So this is a simple example in one dimension of discretization. Okay. Now let's go on to 2 dimensions and see how we could get two-dimensional discretization. Okay. Suppose I have another area here. Okay. In 2 dimensions, I would have to have an x and a y, function of x and y. This over here, and let's see what we can do here. Okay. I think I'll go back here. I wish I could make this over. I'll have to move it to the other side. Okay. Here's the, okay, here we go. Okay. So in 2 dimensions, this would go down, sorry. Here I'd have x and y. And so this would be maybe x here, y here, z here. Okay. And I might have some region in the xy plane. So this x continues this way. So this is the positive x, this is the negative x, this is the positive y, this is the negative y, and then this is the positive z. Okay. All right, so I'll take some region in the xy plane, maybe something like this. Okay. And I have some function that is above this region. So this is a little bit difficult to draw. Let me just do something like this. This is some surface above the region like this. And then I draw these points here. And if I draw the points here, I will get some shape here. And if I want to find the volume here, I need to discretize this area in the xy plane. Okay, so let me show this area from the XY plane. So I'll just give an XY plane view. Okay, so I won't show the Z direction, only the X and Y. So here's X and here's Y. Okay, and then my shape may look something like this. So I want to break this up into smaller areas. If you remember when I did in one dimension, I broke the interval up into small intervals. So I have this interval from 0 up to L, and I broke this into small intervals. Now I don't have an interval, I have a region. So it's much, in 2 dimensions, it's much more complex. Now it turns out that with finite elements, you discretize using triangles. Typically, you discretize using triangles. And this is called a mesh. It's called a mesh. So if I try to break this up into small triangles, triangles may look something like, well, let me put some points on the boundary. I'll put some points on the boundary, and then I fill in the region using triangles. Okay. All right, so I'm not sure how I'm going to do this, but I'll just make some triangles like this. Okay. Okay. Many triangles. This may take me some time to do, so I may not do the whole thing. But you can see that I can create a large number of triangles that can approximate this region. Okay, and I would do this throughout the region, right? And here I can do something like this. Okay. Okay, and and continue. Okay, all right. So here's an example of a discretization that might be used in finite elements. So that's what I mean when I say discretization. So we may see some example on the next page. Okay, okay. All right, so you model a large body or a region by dividing it into an equivalent system of many smaller bodies. And these are called finite elements. Now, finite element consists of small regions and functions that are defined on those regions. So we'll talk more about that. That's going to be a very important part. So here are some examples of elements. So here's a triangular element, as I mentioned. In 3 dimensions, you would not have a triangle. You'd have this which you would call a tetrahedron. You see the red here is a tetrahedron. You can also do in higher dimensions, then it's called a simplex. So a triangle is a 2-dimensional simplex. A tetrahedron is a 3-dimensional simplex, and higher dimensions would be also simplexes. And you can see the simplex consists of edges and nodes. The nodes will be very important because we use the nodes to define function values. So the main idea of finite element is to take a differential equation and turn it into an algebraic equation. When I say algebraic, I mean a matrix equation. Okay. So algebraic would be a matrix equation of the form matrix times vector equals vector. But we'll see more about that later. So here's an object. You define into elements. You get the nodes. For each node, you will develop an equation. And that will give you a system of equations which you can solve as a matrix equation. So here's some example of elements. Here we have a beam with a square cross-section. It may be difficult to see, but there are green lines here that are showing the different elements. And these elements are what we would call prisms. There's a triangle here, and then it goes down by these lines to a second triangle down here. So here the beam is divided into prisms, right? So here you can see also this area is divided into triangles. They're a little difficult to see, but they're there. Okay. And here's a more complicated set of more complicated mesh to describe this mechanical part. So these are some advantages I also mentioned. Let's see. I think I'm going to skip this. We will get into more detail about the finite elements later. But right. So let me ask again if there are any questions. All right, let me see again. I want to see people to respond in the chat just to make sure that people are still there. So please respond in the chat if you're still there. Hello? I don't see anybody in the chat, so please give me some indicated in. I see 2 people. I see 2 people, 3 people. Okay, 4 people. Okay, 5 people. 6, 7. Okay, I should get at least 10, I think. Okay, 8. 9. All right, that's good. All right, so in order to be able to work with finite elements, you do need to have some basic knowledge with vector spaces. So we will be working during the first few classes off of these exercises. Now, because the course is so brief, we will not be able to do all the exercises, but I strongly recommend you to do all of the exercises yourself. So let me see if this download is going to work. Okay, all right. So my first set of exercises is vector space concepts. So I'd ask you also please to download the exercises from the Canvas page. All right. So what we're going to do now, is to break into groups that you can discuss the answers to some of these questions. These are some basic ideas about vector space. And I want to see if you have some familiarity with these. So please, if you can answer the question, you can answer. If you cannot answer the question, you move on to the next question. Many of these are questions about definitions. Okay. Basically, a vector space consists of mathematical objects called vectors that can be added and multiplied by real numbers. So my first question is a vector space also a group? Group is another mathematical concept. So I want to know if you understand the relation between these two concepts. Okay. Exercise 2. A set of polynomials in X with real coefficients can be considered either as a vector space or as a ring. What's the difference between these two mathematical structures on a set of polynomials? So if you've had a course in algebra, which I think you should have had as an undergraduate, you have seen the concept of group and a ring. So I want to know if you understand the relation between group, vector space, and ring. So those are 2 questions. Next question. This is to see if you understand some basic ideas about vectors. Give example of a linear combination of vectors in 2-dimensional space R2. Exercise 3, what's the definition of a linear independence of a set of vectors, V1 through Vn? Question 4, what's the definition of the span of a set of vectors? Okay. Unfortunately, I have the numbering here wrong. You could call this 4a and 4b. Question 5, exercise 4b, what is the definition of dimension of a vector space V? What is the definition of basis of a vector space? What is the relation between dimension and basis? What is the standard basis in R2, R3, and Rn? Let Rx be the vector space of polynomials in the variable x. What is the dimension of Rx? And give a basis for R of x. Okay. an exercise, and the last exercise in R3, given the vector 3, 4, 5, find the components of the vector relative to this basis. What property of basis guarantees you can find a unique solution? All right, so what I'm going to do is I will break you into different groups. You can discuss, and we will do this for maybe 20, 25 minutes. See how many questions you can do. There are 10 questions in 25 minutes, so that's like 2 minutes a question. And I want to see what I want to see about your knowledge of vector spaces. Okay, so are there any questions about these questions that I'm asking you? All right, if no questions, I will break you into groups, and I will try to visit your different groups. I'm going to put 4 people in each group, and you will be put in the groups automatically. So what I would like you to do is I would like at least one person in the group to write down your answers. We can also have more than one person write down answers. No, I'm sorry, let me say it this way. I would like everyone to write answers because I will ask everyone to submit answers at the end of the class. So please, in your group, you can discuss the answers, but write your answers yourself. Okay, so let me say that. So